All right, another worked example here. And this is kind of a flashback to the plane dropping a package. In this case, this is a relief package to a desert island. Okay, so if you could go to the slide that says getting food to a desert island. A Red Cross relief plane needs to drop several aid packages to a group of survivors named Jack, Kate, Hurley, Charlie, Sawyer. 1 point extra credit for the first person to send me an email about what that's referencing. My favorite TV show of all time. On a remote island in the Pacific, the plane has an altitude of about 300 feet and is traveling at about 127 miles per hour. Ignoring air resistance, how far away should the plane be when the Red Cross crew releases the packages? Okay, so let's make a little plane here. Right, and we have the island over here. Right. Right, little people. Guys, I gotta say, that's like the best I've ever done. It's kind of amazing. Okay, right, we're dropping this package. Right, it's landing over there. Okay, I'm gonna write my 2 laundry lists right here. So we have X and Y. Okay, and we have a VX1, a VX2, an AX, a DX, and a time. Okay, and we have a VY1, a VY2, an AY, a DY, and a T. Okay, and I'm also going to write my 3 kinematic equations. So I have V2 equals V1 plus AT, and I have V2 squared equals V1 squared plus 2AD. And I have D equals V1T plus 1/2 AT squared. OK, I think I have everything that I need to solve this problem. All right, so what is my initial velocity in x? Right. So remember, in this case, we have a Vx to start out with, right? That's our Vx initial, right? Now there's no Vy component because it's just being released, right, from rest. So Vy will be 0 here. Vy1 will equal 0. So I'm going to put in 0 over there for my Vy1, right? Now this package, though, is initially going as fast as the plane is, right? So the package should have the same velocity as the plane to start out with, okay? And that velocity is 127 miles per hour. If I were to check my notes and consult with Siri, I would have 56.8 meters per second when I convert that. Feel free to check my conversion, right? Now, we know that the Vx component never changes the entire time. Same z's, same. All right, so that's going to be 56.8 again, because there's no acceleration, right? The distance is how far away they are, right? That's what we're looking for. How far away do you have to be? What's that distance such that when you release the package, it'll land right there on the peeps, okay? And I feel really bad. They don't have arms. Okay, that's better. Okay, so what is our final velocity in the y direction? Well, we don't know. We get solve for it, but right now we don't know, so we put a question mark there, right? What is our acceleration in the y direction? Well, it is going to be negative 9.8 meters per second squared, right? I'm going to forego the units for now, I think, because you guys know what they are, and I want more room. OK, what is our dy? Well, our dy is the height, right? And how high? The plane has an altitude of 300 feet. If I were to consult Siri to find out what that height is in meters, in SI units, it would be 91. So this is 91 meters high, right? So the plane is 91 meters high in altitude, OK? All right. Now, this looks pretty good to me, OK? Remember, I recommend always just finding time first. How long was this package in the air, OK? Whether you need it or not, just start flexing for time, OK? So we have here, we have a Vy1, we have an A, and we have a D. Can we get time? Absolutely, if we use this equation, OK? So let's do that. Let's say my D is 91. But we have to be careful because it's going down, right? Whenever your displacement is lower than it was before, that has to be negative, right? Some of you may have caught that while I was writing it down. If so, mad props. OK, we have negative 91 equals v1, which is 0, times t, plus 1/2 negative 9.8 t squared. OK? That obviously goes away because that's 0. We have negative 91 equals 1/2 of 98 is negative 4.9. Sorry, 1/2 of negative 9.8. OK? And then we just want to divide both sides by negative 4.9. Signs will cancel, right? And we will get a time of 4.3 seconds. OK? And now that's true in both dimensions. We put 4.3 seconds here and 4.3 seconds here, right? OK, that's half the battle because now we basically have filled in everything, all right? So how are we going to get our dx? How far away the plane has to be to release the package so that the people get it? Well, we just say now that we could use this equation. We say that dx equals v1t, which is 56.8, times the time that we just calculated, how long it was in the air, which is 4.3. And now we have the very simple and glorious answer of 244 meters, so that when the pilot's in that airplane and he sees that he's about 244 meters away, he can say, drop the package, and all the cast members of my favorite TV show get to live another day. OK? All right. Review that as needed. On the next slide, it says, wait, are human cannonballs really a thing? And I actually did some research on this and found some videos. And they are. And it's crazy and kind of cool. And I put that video inside of our module for this week. OK? If you can go to the slide that says a projectile motion shortcut. So we just found a range, right? There's a shortcut to finding the range if and only if it's the sort of situation where the object is launched and lands on the same height. So if you have an object launched at h equals 0 and then also ends at h equals 0, then this r can be calculated with this formula on this slide. OK, I'll just write it again right here. Right? If this is the situation happening, right? In other words, you are launching and landing at the same height, then r is always just your initial velocity, right? Not the component, but the actual magnitude of your initial velocity divided by gravity times sine of twice the angle that you're launching at. Now, I encourage you to use this in this situation, but to be very careful, because one time I gave a question that was like this, where it didn't start and land at the same height, and people used this formula and got it wrong, right? So be careful. I put that warning there at the bottom. OK? So I think that's probably enough for this one video, and we'll keep practicing in the next couple. OK? All right. See ya.